but we'll change the focus of what we're doing a bit so that it'll help with your programming skills while not making the electronics part of it get in the way too much. So you should have at this point downloaded and installed the Arduino IDE. Give me a green circle if you did that. Okay, Sargon and Mikhail. Okay, Mikhail, I didn't hear you. You turned your mic on, but I didn't hear you. Nope, not getting any sound out of you tonight. Okay, so I'm assuming everybody except perhaps him got everything installed and ready to go. What I want to do first is I want to open up the environment. You get a splash screen when you click on the icon. And a little window looks like this should come up. Now, if you didn't do anything to it, right now your Arduino should have two lights. It should have a green light on, which is the power light, and there should be a flashing yellow light on it. Does anybody not have that happening? Okay, what we want to do is go to File, Examples, Basics, Bare Minimum. Load that. A new window will pop up. You can close the old one. Now, the arrow key in the IDE is used to compile and load a program onto the device. The check mark is used just to compile it. Just hit the check mark for now, and you should get some things written below. You may not have gotten as much as me, but that's okay. Now hit the arrow key, as long as you didn't get any colorful messages down here. And it should load onto your board. And the net result will be, when you're done, basically you have the light on, but it's not blinking. Give me a green light if you got that to happen. Okay, that's most of you. This program was under File, Examples, O1 Basics, Bare Minimum. You load it, compile it, and then load it onto the board. Okay, now what we're going to do is we're going to reload the boot program again from scratch. So go File, Examples, Basics, Blink. Load that guy. So he brings up a window. You can close the old one. Now, before you compile it, go to File, Preferences. And in here, next to where it says Show Verbose Output During, make sure that both completion and upload are checked. I'm sorry, compilation, not completion. Compilation and upload are both checked. You can close that window. You can recompile it. Now you should have the same number of messages I have. You know it compiled correctly when you see down here the sketch uses some number of bytes of program storage space. That says the compile worked. Now hit the load button. and it should load it onto your board. You'll get some white messages, then you're going to get a bunch of stars and things, or I guess they're hashes. And when it finally comes down to the end, it's going to say some number of bytes have been verified. So when you run this arrow button, it automatically does the compile one more time. It loads it onto the device, and then it rereads it off of the device to make sure what it loaded successfully. Now, if it's not loading for some reason, you need to go to Tools and verify the port number matches where you have the device plugged in. Now, I only have one port, so of course I have the right one picked. You can verify where you're plugged in by looking down in the bottom right-hand corner. There should be a little message down there like a subtitle. This has to say the same port number here in case you have multiple ports. But since most of you had it automatically working, you should already have had that correctly hooked up. Okay, so we're back to square one now. Was everybody able to accomplish that? If you weren't able to accomplish that, give me a red circle right now. Okay, let's prove to ourselves that we have it working. In the code here, it's turning the LED on, it's delaying, it's turning the LED off, it's delaying. Let's make the amount of time it stays on be twice as big. Change that to a 2000, and let's make the delay after it's turned it off only be a 500. Now, you can't save it under the same name because it's an example, and you're protected against overwriting the examples, but we can compile and run it. Just try the arrow this time. It'll do the compile and fail during the compile if it didn't work. And when you have it working, it'll be on twice as long. It's actually on 4 times as long as it's off. So just verify that that actually made that do that on your board. I'm telling you, you guys are brilliant. Okay, now let's talk for a second about what this environment is right now. What we're doing when we run these sketches that we write here, which are written and have as a final part of their name, you can't see it on the name here, but this is called blink.ide or INO, which is the file type. What we want to do is we want to cause assembly language to be executed by this environment. To do that, we're going to have to write the absolute minimum sketch we can and have it call an assembly language program. Now, one of the things that happens on the Arduino environment is in order for it to work, because it's kind of a watered down version of C++, they arrange the hardware to have certain non-default conditions. So one of the things we're going to do when we initialize our assembly language is we're going to undo all of the things they did to make it Arduino friendly. So basically what we'll do is we'll start a small sketch. The sketch will be written as an Arduino program, but all it's going to do is basically call an assembly language routine. When it does, the assembly language routine will undo anything that the Arduino environment did prior to calling its 2 methods. All these programs have 2 methods. The first one is called setup. It runs one time right after you press reset. It actually has done a bunch of things that they don't tell you about, but as far as you're concerned, when you hit reset, This runs one time. Then the loop function runs forever, at least until you reset or turn off the power. By using the loader, it's programmed into your device, so if you turn your device back on and don't reload it, it will rerun the same program we previously loaded. And we'll take advantage of that with our assembly things as well. Now, the Arduino environment was written for people that aren't really real programmers. It was written for people that need to do enough programming to get some maker project working, where a maker is somebody that builds gadgety type of devices and things, which are not bad things to do, but they're just not hardcore programming as you guys need to be for the development environment. So anybody have any questions right now about Arduino? Arduino supports much, much more than the ATmega chip that we're using. One of the chips it uses by default is the ATmega chip, and they call that the Arduino Uno, U-N-O, means one. Okay, you can close that window now. You may say, do you want to save it? Say no. Now we need to go to the website and download a file. Let me remember what it was. I think I'll make this bigger in a second once I verify that's the name of it. That's it. So you want to download the file. Oops, I think nope, I didn't make a copy of it, sorry. When I Control-C'd it a while ago, I had to control something else. You can do that. When you get this file, unzip it, and inside of it, you should find a folder called Labs. Make sure that folder is available on your desktop. And give me a green circle when you have that done. Now, because this is Arduino and the environment is set, it will run on Mac, Linux, or Windows. It doesn't matter. So as long as you have a proper computer, we'll be able to develop. Now, we would, if everybody was having Windows, which would have been nice, then we would have been able to all work with the same framework. But because some of you don't have that type of computer, we need to support the others as well. Okay. Open up Labs and open up the Lab 0 folder. Inside the Lab 0 folder will be a file called lab0.ino. The name of the folder and the name of this INO file have to be the same. So if I create a folder called Fred, somewhere in the folder there'd be a fred.ino. It's the only piece of Arduino we're going to use. If you double click on it, if you install things correctly, you'll get your splash screen. And up should pop a Arduino program. Now, this doesn't look anything like an Arduino program. First of all, it has a main method that calls a function called bridge. I think Bastaine's gone nuts on us here. He's given us a program that doesn't look like an Arduino program. Well, the reason is under the hood, Arduino environment actually compiles that program we wrote with the setup and loop inside of another program, which contains a main program that calls setup and calls loop. So it calls setup once and calls loop forever. So we can simply replace that main function with our own function. And we won't call those. Instead, we're going to call a function called bridge. Think of it as the bridge from Arduino to assembly language. We're bridging the gap. So when we run this, it's going to find a method called bridge somewhere. Where is it going to find it? Well, bridge is external to this code. It also uses C linkage conventions, which is fine. For assembly, normally you would use C linkage conventions. And it's defined as simply being bridge returning a type of void. So in some other file, we're going to find that. Now, if you notice across the top of the environment here, there's 4 or 5 other files. One called bridge, one called code, one called USART, one called util. We want to look at the one called bridge. Now, this is an assembly language program. If we look in our folder, where did I put those? You'll see that all the other files in here end with a .S. The capital letter is important because we want this to run through the preprocessor prior to going to the assembler. And we actually do that because the very first statement is a preprocessor statement. It says include from the include library whatever file is at avr/io.h. Now, io.h is a generic file for including all of the headers for all of the CPUs, microprocessors, that Arduino supports. Inside it, it tests to see which one you're using, and it gives us the one that we need. Now, I don't believe I saved a link on my desktop to it. I'll look and see. I might have over here. Remember looking at this file last time? With all the pin names and the data direction registers and things? This guy is indirectly included in all of our files by this guy. Well, we wrote it in a way that if we ever wanted to change what our main processor was, this would sort out what it needs to do to make it happen. Now, this is our first piece of assembly language code to look at. So think about it as we go. Kind of try to merge it into your mind tonight. Don't wait to look at it later and learn it later because you'll get way behind on the other things we do. Kind of learn as we go. Well, what is this going to do? Well, it's going to create a section called text. Now, text means to the assembler and linker that this section consists of executable instructions, and in our machine should be put into the flash on the computer. We'll see other sections and some other example programs we look at. But text means this is program code, meaning it's going to have instructions in it, and we should put this in flash. Now, inside of that, we have a label bridge. Because the label needs to be visible to this program here, where we said it's an external label, we have to tell the linker and the assembler that that word is a global name, meaning it can be seen by other programs. So it's right there that we made the connection between this word bridge and that word bridge, which gets called down here. Now, in this label, we have a bunch of instructions with an end instruction. All of these commands that start dot something are what we call assembler directives. They don't generate executable code. Instead, they generate messages and things that the assembler and the linker need to know about. Now, inside of Bridge, we're going to do two things. We're going to do a relative call to a method called usart_init. Because this is an assembly code, we don't need to make it global. We'll be able to see it. A relative call means we can use a shorter call instruction because it's within the reach of our branching mechanism. We don't have to do a big call where we have to replace section names and things like that. Once we've initialized the USART being a universal serial asynchronous or universal synchronous asynchronous receiver transmitter. This is the RS-232 communication where we can communicate ASCII data from our program across the USB to any programs we have waiting on the PC. Once we've initialized the USART, we're going to call our code. If we ever return from code, we're going to jump to the label 1 that's behind us. Well, this is the one that's behind us. So we'll stay in a tight loop here forever if this piece of code ever ends. So that means we'll never fall back into this because bridge never ends. If we did, this would just fall off the end, and the way the code is written inside of C, it does an automatic reset and tries to run it all again if you fall out of this method. But we won't. Instead, we'll initialize the USART and anything else that needs initializing, and then we'll call the Axle executable code. Then we'll run this and just loop back and forth here till the cows come home. Anybody have any question about this little chunk of code right here? Robert?
So when you say this R jump 1B, is that just saying it's on line 10 and we're literally going 1 backwards to line 9?
No, these line numbers over here are just simply the line number of the code. All this says is look for a label that comes in front of this instruction that's a 1. Well, there's a label that's a 1. If this had an F, it would say look for a label beyond this instruction, which is a 1. We don't have any of those.
Oh,
Does that make enough sense to you?
So it's calling line 10 because the label 1 is
not
on
calling
line
10. Forget about line 10. It's calling label 1.
Right, yeah.
Which happens to be on line 10.
Right, that's what I meant.
Okay.
All right, thank you.
Anybody else have any questions? That also means we could have lots of label 1s inside of one program, because this will go to the nearest one that's before it. Would we do that? We might, because these might be included snippets of code where we needed to do some branching. If we added them multiple times, we'd want to be able to use the same label over and over, which we can't do with an ASCII label. We couldn't have multiple bridges, but it's smart enough to know that if it's a number, we can use it multiple times because the call will say whether it's forward or backwards of where we currently are. Okay, so let's look at the initialization code for the USART. In here, we've got a global label called USART init. We had to make it global here so he could see it. But nowhere in here do we have to declare that we're going to be looking for it. This does make it available, though. Again, we have a section called text, meaning there's going to be some executable code in Flash, and we're going to do some stuff. We'll come back and talk about the details of this when we're ready to use the USART. Now, that being done, we're going to then execute code. Code has three sections: a BSS, a data section, a text section, which we know is Flash, meaning code will follow, a declared global name of code because we needed it when we executed it over here, And once we've executed these two lines of code, we go into a loop where we basically jump to forever. Now we wrote in here as well an interrupt function that will be used later in other code when we want to receive a character. We'll talk about it when we need to. It's not necessary in this program, but we put it here in case we ever use this as a model and make it bigger for other purposes. We also take advantage of two functions which are in the C library. One of them clear out the BSS, and the other copies data into the data section. Now let me explain that a little bit with the two types of sections we have up here. The BSS doesn't stand for anything. It used to, and people have long since forgotten what it stood for. But basically what goes in this section is uninitialized data. Uninitialized data, meaning that it's going to ultimately be measured out inside of the static RAM, in the SRAM. It'll have initially, because we call this statement, it'll have a value of 0 in every byte. We didn't call this, it could have random values. We made it zeros just to make it clean. Data, on the other hand, is going to be initialized data. Now it does it a little tricky. Basically, you're going to declare a byte of data and a label probably, which is going to be mapped into the SRAM. Because it's initialized, that doesn't mean you can't change it. It just means it's initializable. Then the initialization number, because there's nowhere else to put it on this chip, will be put behind the program in Flash. Then upon starting up the code, this function will automatically copy the initialization value from Flash into the correct place in SRAM so that the data will appear to have initial value. A little bit tricky, but once you get used to it, you'll love it. And then, of course, we know the flash memory is where the real instructions go. But we also have that initialization memory. We'd have to look at the .hex file to see that in action, and we might in a week or so once we really have some of this under our belts. Now, we have one more little piece of code over here, which is a utility function called toHex. And what it does, it takes a byte of data and it turns the two nibbles that are inside of it into two ASCII characters so we can print it. We'll come back and look at this and go through it line by line when we need to be able to do that. Now, because we used main and called bridge directly, We did not call that initialization code that causes things to be misaligned for us. We fixed things by just calling bridge alone here. So we will cause the thing to be loaded. This method will be called every time reset occurs. It'll immediately jump into assembly. Assembly will immediately initialize the USART and then call the code we need. And if the code ever finishes, it'll just stay here hanging around forever. In our code we've written, that doesn't happen. We do a couple instructions and then we stay here forever instead. Anybody have any questions about this program? You might be saying, well, it sure doesn't do much. Well, it does these 2 lines of data here. It sets a bit, and then it sets another bit. Where does it set the bits? Well, it sets bit DDB5 inside of the DDRB register. It sets port B5 bit inside of the port B register. And we'll go over what these data registers are in a couple minutes. But we also see that that port has been wrappered with that piece of macro code here. What that code says is, I need an IO address. Remember, we have 2 types of addresses. We have IO addresses and we have memory addresses. Well, this instruction needs an IO address. Remember, it's one of those special instructions that only works in the first few bytes of memory. So this value right here is going to be in memory, meaning it's going to be 20 hex too high. So this code here takes care of subtracting away 20. So this guy is actually working with the correct value of DDRB when it puts this port in it. It's going to set a bit, set another bit. Now, what I can tell you is, before we go into the details of this, which we'll do on the next little chunk of code, setting a bit in the data direction register for a port makes the bit you set, write this down, an output bit. Meaning DDB5 is going to become an output. Setting a bit inside of port B while it's an output says we need to turn this bit on port B, bit number 5. And if we look here, port B5, we'll notice if we follow all the way over, it's the yellow LED that's on your board. Now that's the only piece of hardware other than the USART and some other little gadgets we can work with that we'll be involved with for the first few exercises. But basically the idea here is it said, make that pin an output and turn on the light and then stay here forever. Well, we haven't loaded this yet into the box. We have a blinking light over there now. It's still running the blink program, the modified version. So what we can do is make this guy, the lab guy, lab 0, be on the front. Let's assemble it by hitting the arrow key. If it says thank you when you're done, it should be loaded. And if you look at your board, you should see that the green light is on, that's the power light, and your yellow light has been turned on. So that would tell us that if we go to our code, and instead of setting this bit, we clear it, we do a CBI, we load it, we look at our board, that light should be off. If you got that to work, turn your green light on. You can now tell everybody that you're a successful assembly language programmer. Look at you people. Oh, look at all those green circles. I am impressed. Okay. Now notice we didn't add any data here. We didn't have any data here, but I put the sections there just so you could see them and I could explain to you what these two guys do. These are actually called from inside of C, and it's necessary that they run prior to us using those variables. Okay, so we can close that window. We can go in our labs. Go into lab 1. Open up lab1.ino. Okay. If you notice, bridge didn't change. Bridge itself didn't change. Init didn't change. This utility function, we didn't add anything to it. So the only thing that could have changed is the code. Now, if we look at this, this does a little bit more than the last one. Not a whole lot more, but it'll give us some things to talk about because we'll have to learn how the initialization works in a couple of ways. So let's look at our code and see what's here first of all. We have no uninitialized data. We did, however, create a string. Notice it uses double quotes. Any special formatting, like a new line, we have to add ourselves. And we put it in a data field. Notice that this is a assembly directive. It's the word ASCII, but the second I is replaced with a Z. Now, it's totally legitimate for that second one to be an I, in which case, same thing, and the ASCII codes that are generated are identical. But if you change the last I to a Z, it does one extra thing. It takes one more byte than you wrote and puts a binary 0 in it. So we have a string that's terminated with a 0. That way, if we want to print out what's here, when we get to the 0, we know we're done. So quite often we'll use the ASCII Z. Just remember, it takes one more byte than this did. Remember, this itself is only 1 byte. It's a new line character, which we memorized on night 1 to be a hex 10. This is the name, my name. Well, let's change it to be whatever your name is. So go ahead and put your name there. Because I'm thinking nobody in this class's name is Billy Bob. And then let's look at the code section. First thing we're going to do in the code is we're going to set B5 to be a 1, meaning we're going to turn the LED output into an output, the pin into an output. Second thing we're going to do is we're going to turn on that light. Then we're going to, it looks like, do a loop to print out the name and go to forever where we loop forever. And we still have this down here that we didn't do anything with, where we're going to receive a character And we didn't do anything other than we just make a note that they're still here. We're still going to clear the BSS, and we're going to copy from below the program into data memory this name right before we execute. So it'll get moved from flash into SRAM. Now, before we talk about handling the string, let's talk a little more detail about the port pins that are on the Arduino. Let me do that and grab a text window here. And I guess we'll come back to that in a minute. I believe last class we talked about the fact that on the ATmega 328P, we have 3 different ports. We have a B port, we have a D port, and we have a C port. One of the bits of the C port is up here and rarely used because it's hooked to the reset pin. So we do have a C port, D port, and B port. Now we're interested right now in the B port because that's where the LED is attached. We're also in the 6th pin on that port. Well, 0 is the first, so they're off by 1. So 5 is the 6th pin. So we're going to be working with port B. It's going to be an output, and it's going to be the 5th number, which is the 6th pin. So let's look at that again. Actually, we can look at it probably best inside of the documentation. What I'm going to do is go to the registers here. And I'm going to make a note that port B, port C, and port D are all in the lowest part of memory, which is good because that means that I'm able to use the SBI, the CBI, the SBIS, and those instructions we talked about last time, which are only able to be used inside of I/O space. When you use them in I/O space, they need to have these addresses. But if you look at them in the header files, they're always going to have the memory address. So in order to use those instructions on these particular registers, we have to first of all subtract away hex 20, which gives us the real I/O address in order to use those instructions, which is exactly what we did in the instruction we wrote. As you recall, see if I have that still open here on the screen. This says basically we want to take the address that's in parentheses and turn it in from being a RAM address into being an I/O address, which on this machine means subtract hex 20 from the address. And we need that because that's the type of address this instruction uses. And we can look that up in the data sheet to see. Basically, a set bit I/O or clear bit I/O would be the name. The I stands for input output. Now, if we look at these, we're worried about port B. But along with port B or any of the ports, we get 2 other registers. So when we're looking at these, we want to be aware that we have a DD register. We have a port register. And we have a pin register. Now, I may have written them out of order from what's here, but that's okay. So the data direction register allows us to set whether or not a particular bit is input or output. Now, I'm going to break this into kind of a tree as we go along here. If we read from the register. We're going to be reading what the data direction is. So once I set it to something, I can come back and check it by reading that register. However, if I write to the register and I write a 0, I'm going to make the register be an input register. This also is the default value. If I write a 1, I'm going to set that bit to being an output. So initially, the data direction has everything set to be inputs. That way they look like they're floating or high Z to other devices that might be attached to them. Now, it gets a little more complicated than this, but fortunately, once you've kind of memorized it, it's quite simple. With a port, we can do reads and writes as well. You read, you do a write. Now, if we read from a port, regardless to whether we're input or output, we read from it. What we read is something called the output buffer. Now, if we're in input mode, and we write, we can write two things. We can write a 0, or we can write a 1. If we write a 0, we deactivate pull-up resistors. However, we write a 1, we activate pull-ups on that particular pin. If, however, we're in output mode, we write a 0. We drive the pin low. We write a 1. We drive the pin high. So anytime we read whatever was written to the port the last time. That's our output buffer. However, if we write, it matters whether we're doing input or output. If we're doing input, set our port to input, but we write to the port, we turn off or on the pull-up resistors. If, however, we write while we're in output mode, we do what we expect it to do. We write a 0 to the port, we get a 0 on the pin. We write a 1 to the port, we get a 1 to the pin. Now the pin register is physically hooked to the pin. So there's two things we could do. We can read it, in which case we simply read the value on the pin. If we write it, there's two things we can write. We could write a 0, or we could write a 1. If we write a 0, nothing happens. We write a 1, we toggle the pin. Now, conceptually, the best way to think about this, because it does get a little complex and you'll forget which one does which, so I always keep a little piece of paper laying around that outlines these modes for me. Because I can't remember all the machines I know. I just have to remember while I'm using it. So, data direction, basically its main function, is to say, is the pin an input or an output? When we're an output, the main function is to write to the port, which in turn will change the pin, if it can change the pin. Somebody else may be driving the pin stronger than we are, in which case it won't really change. But whatever we write to the port is what we think we wrote to the pin. Finally, we can read the pin if we're in read mode, and we'll see what the value on the pin is. We can't change it if we try to write directly to the pin. What we do is toggle the pin. The value of the pin changes to the opposite of whatever it was. So in our case, we needed to set it to output, which put us into data direction into write mode, is what we're going to set our port now, to output a 1, which means drive the pin high. Didn't do anything fancier than that, but we needed to know all those things in order to do the right things. Anybody have any questions about that? If left alone in a room with a pen and a data direction register, would you know what to do with it? MacGyver would. Okay, give me a green circle if you got most of that written down. Okay, that's most of you. Now on page 100, I guess we can find it over here. Yeah, page 100, we actually have the registers laid out for us. The 0 register is on the bit is on the right. Register 7, or the 7th bit, is on the left. Port, data direction, pin. Notice the naming convention. The port is followed by the B, C, or D of its name. Individual pins on that particular port will have the port name followed by a number, which is a 0 relative number. Now in these charts, if it can be read or written, there'll be an R/W. If it can only be read, there'll be an R. Only be written, there's a W. If there's a dash, it means can't change it at all. Nothing can happen to it. You can't even look at it. Or it's unallocated. Notice that the initial value of all the port values are make it low. So if we turn our thing from input to output, we're already going to try to write all zeros to the pins. This happens every time we get a reset. The data direction is also 0. Does 0 mean input or output? Scott, what do you think?
0 means input.
That's right. Now, let me tell you an unfortunate thing here. Remember, Microchip bought Atmel, and they now own them. Well, Microchip has very similar microprocessors. And it's kind of a joke at Microchip, because if you want to use their data direction register, if you want an output, you set it 0. If you want an input, you make it a 1, because the 1 looks like the I in input, and the 0 looks like the O in output. Atmel does it just backwards to that. And you just have to remember that if you want an output, you need a 1 because an I doesn't look like an O. And the opposite. So yes, indeed, this is they set the inputs. Remember, inputs make, without any else happening, I'm going to make it look as though it's a high Z output to anybody else looking at it. although we would be an input able to see anything that changed on the pins. Now the pin is literally hooked to the pins. So there is no default because we don't know what the pins are. Whatever value they have, that's whatever you're going to see if you read the pin. What happens if you write to the pin? Robert?
Either nothing or it toggles.
Yeah, if you're writing to it, it's going to usually toggle because you're probably not going to write to it otherwise. Good, excellent. Now, the one thing you have to remember with that is you may make it toggle, but if somebody else is driving the pen, then you have to pay attention a little bit on outputs to whether or not it's hooked to a bus or whether or not it is using the same technique that we would have used with an open collector output. Now, this particular device has pull-up resistors. Let me see if I've got that somewhere handy here. In the world of tri-state logic, where we have multiple guys trying to write to a bus, we take away the totem pole part of their output, leaving them only with the ability to ground the wire. Meaning he could ground it, or both of them could ground it, and the wire would show ground. Any other time, it's just floating around showing whatever it wants to show. So we attach an external pull-up resistor to perhaps 5 volts. Then when neither one of these guys are driving it to ground, anybody else looking at the bus, so he's reading the bus, will see 0 or 5 volts. If they're driving it, they see a 0. If not, they always see a 5 volts. On the AT Mega chip, we could still do this, but for our purposes, we solve a different problem. As an input, here's my pin coming in. Let's assume that I have a button. And when I push the button, I want to ground the signal. Well, remember, this was as an output. This is an input, which we would use on this. What's going to happen when I push the switch? Well, I'll see a 0, won't I? However, when I'm not pushing the switch, what do I see? I have no idea what I'm going to see. It could be anything. So what I do is I externally put another pull-up resistor on this, similar but different conditions. This time I'm using an input. That time I'm using an output. They do serve the same purpose of having put the tri-state thinking on this box, but we'll keep it separate. So when I'm not pushing the button, I see a 1 because this is pulling it up to a 1. When I do push the button, because I have a resistor, current can flow, but I'm right at the ground, so I'll see a 0. What I also have is on all of my pins, I have the ability, let me not draw it this way, this will confuse you. I have the ability to pull it up internally to plus 5 volts. That was those pull-up resistors I was talking about. That's the same as having this here, meaning I can hook things out here that aren't hooked to anything, and when they go to ground, we see a ground, and the rest of the time, because I'm pulling it up to 5 volts, I see the 5 volts. So if I don't want to add the extra component to my design, I can let the chip do it for me on each pin, individually controllable, and I can turn them all off at once if I want to do some sort of bus management with them. So where we had that one thing in design here that said, I need to be able to deactivate or activate the pull-ups, that's what I'm talking about. Activating them means I have something external that perhaps can only drive it low, and I need to pull it up to 5 volts for all the rest of the time when it's not driving it low. Anybody have any question about that? Okay, dokie. So in our code, we said what we want to do is we want to make the data direction register on port B on bit 5 be set. The register's name is here, and we'll match the first part of this. Notice there's no R here. Now, port B, port B5. It's the matching pin. Because we're using the SBI instruction, which, as you remember, as we mapped out memory, is the only thing that can get to those first low bytes of memory. I don't think I have the that graphic here on my computer right now. But actually, I probably have it laying in the chair over here somewhere. In the range 00 to 1F, we have our regular registers in memory, but those same registers, 00 to 1F in I/O space, line up with 20 through 3F. And there's only 6 instructions we can use: SBI, CBI, SBIS, CBIS, and in and out in those ranges. And the 2 that set and clear the bits are SBI and CBI. SBIS and SBIC have to do with branching, and in and out actually do things a byte at a time. So while they're input-output instructions, they don't have this ability to protect all the other bits while they're changing one bit. So the next thing we do in our program is we're going to print out the name. And it looks like we're going to, if we just read kind of with our eyes fuzzed up, we're going to initialize some data, go through a loop, looking for a 0. When we find it, we're going to go to forever and loop there forever. So let's see what we're going to actually do to make this happen. First of all, we have to load the address of my name, because we're going byte by byte, we need its address, into a register. Well, since it's going to be a 16-bit address, it's actually less than that because we're only going to be able to address, flash memory, but nevertheless, it's going to look to us like a 16-bit address. Because of that, we need to load the high byte and the low byte into 2 registers. In the case of the 2 we picked, they have to be either the X register, the Y register, or the Z register. If you remember from the notes last time, Z register is a name for the X register, 30, 31 pair. So the low byte goes in the low register, the high byte of the address goes in the high register. Now it could be that the high register is all zeros. We aren't looking at what the register contains, we just need a 16-bit address. Now we're going to go into our loop section where we're going to load into register 16 whatever the Z register points at, and then bump the Z register to the next byte for next time. We'll compare whatever we loaded into 16 with a 0, because if it's equal to 0, we're done. If it's not, we're going to call this method called usart_send, which will send whatever happens to be in register 16 at the moment. And then we'll jump back and loop again. So for every character in our name, including the new line, we're going to send that individually over the usart. Now let's talk about the usart again and how it works. The usart is on these 2 pins down here, receive and transmit. Let me see if I can make them big enough to see. So when we say send something, we're going to use the transmit pin. The transmit pin is going to take RS-232 looking data. It's going to be at 5-volt level, which we talked about either the first or second night of class. We talked about how it's going to add a start bit and a stop bit, possibly a parity bit, and it's going to send it from low bit to high bit, then the parity bit. So it'll be start bit, low bit, through high bit, potential parity bit, and then a stop bit. That'll be sent on the board up to this chip right here. And as every bit is transmitted, we'll see a byte be transmitted. It'll light up. This then converts it into USB, which sends it out the USB port through the USB cable over to our PC, where we'll have to have a program running that can read the USB. Well, the USB actually makes it look like it's RS-232 data. So as long as we can read RS-232 data, then we're able to read the USB stuff that was sent to us. And hopefully then we'll make up some way to print it on our screen. So it's going to come out the transmit pin. If we had data coming in, it would do just the reverse. It'd come over the USB into this. We'd see a receive light blink. It would then go in the receive pin, and then it would cause in our code this receive interrupt down at the bottom here to execute. We're not receiving anything, so we won't talk about this until we do. But just be aware we already have some code down here that knows how to receive data on the RS-232 line. So this seems like it's very doable. We haven't initialized the USART in this code, but we did in the previous code. So let's look at that and make sure we understand what's going on here. We're going to call, in this text section, another function we called USART init. We made it global so it could be seen. First thing we're going to do is we're going to set the baud rate, which is the number of bits per second, in our case, to 9,600 bits per second. Baud is an old word which was meant on old machines, how often it changed per second. Bits per second is real. It means how many bits per second we need. Baud is really a method of telling us how many electrical changes are there per second, from which we derive bits per second. Because we might have a baud rate which is, half the speed of our bits per second because it has 4 levels it can transmit at, 0, 0, 0, 1, 1, 0, and 1, 1, meaning we could have 4 levels transmitted in 2 bits. So we use baud rate in ASCII terms, but we mean bits per second. So what we're going to do, it looks like, is we're going to take 2 bytes of data. We're going to load one into register 17, another one into register 16. Then we're going to store those 2 registers at these 2 addresses on our board. So let's see how that would have to work. We're looking for UBRR0. A bunch of these in here. Let's see if I can get to it quickly. It would have been easier just to go back to the, let's go to the end down here. Yeah. I'm scanning down these names right now. Okay, I missed it. If anybody sees it, just tell me where that was. Here we go. Okay, we only have one serial port, so it's going to be UBRR0. If we had two of them, there'd be a UBRR1 as well, a high byte and a low byte. Low address gets the low byte, so it's a little Indian. And in here we have a number which stretches across 12 bits. The top 4 bits go here, bottom 8 bits go here. Page 204. Here's the register. The 12-bit register contains the baud rate. And what we need to do is we need to then figure out what value we need to put in this register. And to do that, you come back over here to the code. We have a CF recorded as the value we actually need. Now, there's a table in here, and I hate to go searching for it again. I should have looked it up before class. But let's see if we can find it. Again, I got to search for the same thing, so it's be okay. They don't have the 0 on it in here. We're very close. That's the register itself. Here we go. Okay, how we use the UBRR settings for commonly used oscillator frequencies. We're running at 16 megahertz. We want to run at 9,600 bits per second. To do that, we can use the number 103 or the number 207 and get only a 0.2% error. I believe 207 is the number we used. Somebody check that for me. Turn that into hex. The other guy's not doing it. Somebody do it. Take 207 and turn it into hex. Nante, what'd you get?
I got CF.
CF?
CF.
Let's see what we... CF, sounds good. Okay, so we loaded a CF into 16, so it's all zeros in the top bit. We stored them in the 2 registers we need. Now we've got some other register manipulation we need to do. We're going to take, and in this register here, the UCSR0B. I have to go looking for these again. We're going to be changing this register. We're going to turn on the receive enable, transmit enable, and receiver interrupt. Allow, if we receive a character, for an interrupt to occur. If you look here, there's bits for those. The RXEN, which is here, enable receive, enable transmit, and receive interrupt enable. We need all those turned on. So to do that, we took a 1 and we shifted it left that many positions in each of those cases. We ORed them together, which gave us a bit 1 1010000. Actually, it was 100110000, which would be these bits in order, stored it in this register. Now, from that point on, we've enabled those. Now we have to tell the system how big the data is. We don't want to use parity. We want to send 8 bits of data and 2 stop bits. So we're going to use the C register, which will probably be the next page. Move it up a little bit here. And in the C register here, we said we want to turn on USB S0, which is this guy here, UCSZ01, which is him, and then we wanted to do USC00. So we need to look up in the table. When we turn those 2 bits on and they're both zeros, we're running as a or they're both ones, we're running as an 8-bit character. That's those 2 names. This one was already a 0, so we didn't have to change him. And we had the USB S0. And for S0 turned on, that means we're using 2 bits of parity. Not parity, stop bit. So we load those into register C. Then finally, you remember in that original table when we were getting the baud rate, the number could have been half of this or the full number. In order to use the full number, there was a flag we had to set. That flag happens to be this guy right here, the U2X0 flag inside of register A. So once all those registers are set, we've made our thing be 9600, 8 bits of data with 2 stop bits, able to send and receive, and if we receive something, cause an interrupt to occur. So that was the setup for the USART. And you should work your way through that again on your own to make sure you understand what all those registers were doing. Anything we didn't touch already had the correct value. Now, in our program, we called this send method. We made it global so we could get it. We said we'll send whatever's in register 16, which means 16 might get clobbered, which is okay. Anytime we say we're going to use a register and we know what the contract is, that's valid. So to send the data, we take whatever they passed in and we push it on the stack. We then load register 16 from UCSR0A, which will be right up here. And what we're looking for is we're looking to make sure that the data register becomes empty. We don't know, maybe it's still trying to send the last thing we put in it. So what we do is we do a skip if the bit is set. So if this bit is still set, meaning that the register is empty, we'll skip over the jump back to check. If not, we just jump back to check until this bit comes on, in which case we jump over, we grab 16 again, we pop it off the stack because remember we clobbered it here. We then put it into the output send register and return. And we just leave the device, the USART, to go ahead and send that character for us. If we get back here and it's still not sent, we'll wait until it is, then we'll continue. Everybody kind of understand the flow of the send method? And that all being said, is we've covered all the code that's in here. We know how things get set up. Let's review one more time, passing our way through. Who wants to tell me what this file is for? Every one of our labs will have one of these, and they'll be named after the folder it's in. Robert, what's this file for?
Oh, can you hear me?
Yeah, we can now.
Okay. That's just our way of loading the ASM file. Or the
Right. It's our bridge. It's the thing that's going to get us to the bridge between assembly and C. It basically takes care of getting rid of the Arduino world. So I go to bridge. What's the purpose of the bridge code? What's it do? Robert, give me again.
It initializes the USART and then calls our code.s file.
Why is it important that it do those two things? You can answer, or anybody else.
Because our code is using calls from the USART file, so we need to initialize those first.
Yeah, that's a good, really kind of the real hidden reason underneath all of it is a reset could happen at any time. When the reset occurs, it's imperative that the USART become reinitialized and that our code be started over. It's like rebooting. If you crash, you want it to reboot, but you don't want it to reboot and be writing your files to the network. You want to make sure everything is back to square one. So bridge takes care of getting us back to square one. And it also becomes the catcher in case the assembly program ever ends. We'll catch it here and we'll just loop back and forth doing nothing, which is harmless. So it'll allow us to just harmlessly sit here doing nothing if our other program, and it could wait for somebody to hit the reset button. Remember, on our board, there is a reset button. If we ever got here, we could push that button and theoretically this should run again. We'll test that in a few moments. We don't know if we set up all the code or not. Who knows? Now we're going to call USART init. We just talked about what USART init is. Why are both these two functions in here? Why is this one in here? It has nothing to do with init. I know the answer. I don't have to answer. Somebody else. Robert, you want to try again? Are you the only one here tonight? Maybe everybody else is gone. It's a ploy to me.
I'm guessing it's for modularity and reusability of the code and to clean up our code. It's just making helper functions.
Right. This turns out to be a utility function, but it's so related to the USART, we might as well stick it in with the other USART code. However, the receive interrupt, although it's USART related, is not universal. It's specific to a program. And so for that program, it makes sense for it to be in the program with that code. And so that's why we don't see the USART receive code here. We only see the send code. I just thought how funny it would be if you're the only one that's not here and you're just a recording and everybody else is here, but they just don't talk. Oh, the irony of it all. Okay, so why didn't we use the utility code? Well, very much for the same reason I didn't use my oven today. I didn't cook anything in the oven. So I didn't do anything that needed the utility code. I didn't turn anything into hex. Okay. And we talked about that, and we talked about code itself. In our code, we've got a name. I'm going to change my name from, I'm going to stay Billy Bob for a while. We should be able to load this onto our board. So go ahead and do that. You might have to save it when, I think it actually yours is probably set to auto save. Now, when you do it, you should see something which is a little odd. you should see a green light and your yellow light is on, but nowhere does it say Billy Bob. I've been looking all over both my screens. I don't see it. Well, it's still in the text here. Anybody have a conjecture as why I'm not seeing Billy Bob anywhere? Peter? Peter, if you're talking, you need to get closer to your mic. No, I can't hear you. You're way in the background. We'll get there in a second. Okay. Dante, what's up with you? I'm checking microphones.
Because it's serial monitor, so it's running through the Arduino, but it's not actually connected to anything.
Right,
So on the
there's
Arduino,
nothing looking at the USB port right now. Okay, we, of course, in Arduino world, do have a serial monitor. So we should be able to, if we enter an environment here, go to Tools, Serial Monitor. Pay attention to the fact that it's Control-Shift-M also. Makes it easy to get to. Hit that. That'll throw a reset at your board. Put up a window. And in theory, whatever name you put in should come out, followed by a carriage return or a line feed. Check the values I have down at the bottom of mine. I have auto scroll checked, show timestamp not checked, no line ending, 9600 baud. If you don't have 9600 baud, you'll need to change that. And if you want to clear the input, you can hit the clear input button. That doesn't cause a reset to occur. Closing this window and reopening it does. So I could close it and do a Control-Shift-M. It'll open up and throw a reset at the board again. In theory, I should be able to push the reset button. Look at your board and you should see a little button on there. We're up in one of the corners. I think it's up near the USB thing. You should be able to push. Everybody get the reset button to work? Robert, do you have a question? Or is your hand just still up? It's gone. Okay, and just to verify, you can use your reset button if you like. When you push the reset button, you'll see that the button for sending data flashes. So as you see Billy Bob goes flashing by, it's going to make the transmit light blink. Now, if you have this set to something other than 9600 baud, you'll get garbage on this screen. You'll have to throw a reset at it. We might change that to something later, but this is a good speed for just testing hardware that's not been built on a circuit board or anything like that. Just to verify that everything is working properly, close your serial monitor. Go change your string to something else. I'm going to change mine to I love COS231. -010, I'll narrow it down to this class. Load it, run it, Control-Shift-M. So whatever length you give the string, as long as you don't put any zeros in your string, it'll print all the characters up to that 0. Robert, do you have a comment?
Yeah, I'm getting an error while setting serial port parameters. And Arduino is not doing anything. I hit the reset button, and now nothing works.
Where did you get that message?
In the small console just underneath the sketch.
Okay, but when you did what?
When I hit the reset button. The physical reset button.
Okay, well, close it all and reopen it and verify that you reconnect to your device. And then do the Control-Shift-M. to bring up your monitor, and let's see if it happens again. Occasionally, this will get out of whack. Did that work?
It would seem so.
Okay, good. Okay, so I'm going to change this back. What name did I have here originally? I don't even remember. Billy Bob. And so I have a saved version. Okay, any last questions about this one before we move ahead a little bit? Okay, I'm going to close that window for now. Okay. That was lab 1, am I correct? I closed it without thinking. Am I correct? Lab 1? Okay. So let's open up lab 2. Okay. Why don't you just run your eyeballs over this code, and then I'm going to get with you and we'll talk about it. But I'm going to even mute my mic for a second here, get myself a cup of coffee while you're running your eyeballs over. See if you can figure out what's going on in each of the assembly steps that are in this. In case you were wondering, by the way, if you put on any line, semicolon, whatever follows that is a comment. So as we're talking about this stuff, if you need to annotate things, like, oh, you don't remember what that 0 was, write yourself a little note out to the side. So later on, when you come back to it, it won't be a great mystery. Normally, you wouldn't do that because the code itself speaks for itself once you've looked at this for a while. But for now, since you're pretty much everybody's a beginner here, not all of you, but most of you. Okay, anybody want to give me the global overview of what this program does? Let me ask again, does anybody want to give me the global overview of what this program does? Matthew?
From what it looks like is if you send a 1, it turns the light on, and if you send a 2, it turns it off.
Okay. It might be as simple as that.
Because you're in the code dot capital S, you have a turn on and turn off method.
Mm-hmm. Okay.
And then right above that with the forever, it says turn R16. And I'm going to go on a limb and say that 1 will turn it on. And if it gets a 2, it turns it off.
Okay. I'm not hearing anything bad that you're saying there. That all sounds like reasonable stuff. Let's look at the code, all of us together now, and see if we can work our way through. You all might want to sit next to him. Wow. Okay, him and Robert. Robert was, yeah, and I think I saw Scott's hand up a couple times tonight, too. And Peter's hand would have been up if we could have heard him. I heard him way off in the distance. Okay, so we don't have any uninitialized data in this. We do have 1 byte of data called CH, which is initialized to a null or a 0 value. This will go in SRAM, so it can be changed. Here comes the flash. We know what the global code does, so here's our label. Set the LED as output and turn the light off. Okay, we've seen that enough. We know what those 2 lines do. Now, turn on global interrupts. Set enable interrupt. It sets the bit inside the status register at 5F and it turns it on. And at that point, any external interrupt that we've turned on is going to be able to happen. We've only enabled 1 of them. We did it over in USART init. Remember over here where we added this thing on the end of it? We enabled receiver interrupts. So if a character is received, we're going to go to the interrupt routine, which is down here. We'll talk about that in a second. In any event, forever, we're going to turn the interrupts off so we can't get interrupted. We're going to load from SRAM the character at CH into register 16. If it's a 0, compare immediate. If it's a 0, branch if it's equal, meaning that it is equal to a 0, to next, which will be down below. Otherwise, compare to see if it's a 1. If it's equal to a 1, jump to turn on. If it's equal to a 2, jump to turn off. So branch if equal, compare immediate, branch if equal, compare immediate, branch if equal. Then do a relative jump. This is like a go to. Go to next. Same place we went here. So we only care about the character if it's not a 0. And the only one we take any actions on are if it's a 1 or if it's a 2. So the 0 must have some special significance. Well, if it's the first value, if we see a 0, we know for one thing, it could be we've not received any characters at all. We also, while interrupts are cleared, can't receive any. The only time we can receive any are between that instruction and that instruction, if any are there. Otherwise, CH could get corrupted by an incoming character. Now, turning it on simply says, turn the LED on, we set it on, jump to next. Turn it off says, clear that character, jump to next. Now, in any event, if I ever get to next, I'm going to load immediate into 16 as 0, and I'm going to wipe out any characters that happen to be inside CH. Now, what I just did is imperative because I may have received no character, in which case it's already a 0. Writing a 0 won't hurt anything. I might have received a 1 or a 2, in which case I don't want to receive them immediately again, so I'm going to wipe them out by putting zeros there. Or I might have received something that's not any of those, in which case I want to wipe it out because I don't want it at all. Then I turn interrupts back on again, so I could receive another character, but I won't process the same 1 or same 2 that I already saw because I've changed it to a 0. New character may or may not arrive. If it does, we'll go get an interrupt. If it doesn't, oh well, no new interrupts. We just jump back to forever. We look, we get a 0, we jump out of it and keep waiting until somebody does type a character. Now, the interrupt has two things. First, it has to have its name specified so that it can be put in low memory as an interrupt vector. And secondly, we have to declare the name here so it can be processed when that vector jumps to us. We're going to do an in, which is an input-output only instruction on the status register. So we have to promote its address to being an IO address, which means subtract 20 from it. We'll put the current status in register 2 and push it on the stack so we don't accidentally change the status when we return. We then load into register 2, load into SRAM. I'm sorry, load from SRAM. Whatever's in the register called the USART data register. We pick up any characters that we've received. We know we received one or we wouldn't be in this interrupt. We then take register 2 and store it in SRAM at the place called S at CH. This can only happen when this is running, and this can only run when we're not inside that code that's protected by having the interrupts turned off. We then pop the status back off the stack, put it back in the status register, and return from interrupt. Meaning that when this is done, whatever character was typed will be located inside of the CH variable. And it can only wind up there during the time period between here and there, or the time period between here and the next time we hit the start of the loop, which is immediately. Anybody have any questions about that code? This exhibits to us a character being received. Okay, no questions. Okay, well, let's try running this. Well, actually, first thing we got to do is load it on our board, don't we? Okay, the only light that should be on right now is the power on light. You can do a Control-Shift-M to get your serial monitor up. You may see some lights blink a little bit as it decides, you know, what baud rate and things it's going to do. May I think it received a character. Now, in order to type characters, you have to go inside this little bar at the top. If you type the number 1 and you push enter, watch your board when you do it. You should see the LED come on. Type a 2, LED should go out. Type of 3, light will blink for receiving a character, but we don't process it anywhere. Type of 1 again, character should come on. Type of 5 or something. Shouldn't turn the light out. 2 should turn it out. 1 should turn it on. Okay, give me a green circle if you got that behavior. Robert, you have a comment?
Yeah, just because this is who I am, I decided to try something else, and I put in 11, and it reads it as a 1. So this is only reading one character at a time.
We'll read both characters, right? What if you put in a 1, 2?
That's a good question. I know 2, 2 turned it off. 1, 2 would, blinks on and right back off.
Right, it's reading one character at a time because we're processing every time the interrupt receives a new character. Okay, everybody pretty good with that? Okay, now who wants to explain to me at a high level what's going on during that section of code right there? Scott?
We start off by enabling the interrupts to set up so that we can receive any interrupts, and then we turn them off with the CLI command. Then we're taking what's in SRAM at the address with the CH label, loading it into the register. We're comparing it with 0 to see if it's equal to 0. If it is, then we're branching to next.
Why do we do that?
When we branch to next, we're going to basically clean out that register with 0, reset our memory, and take in another interrupt. Basically, it's kind of like resetting the whole thing so that we can receive the next interrupt or just sit there.
That's exactly right. If we didn't do that, we would just keep receiving the same character over and over and over again. In this case, it wouldn't matter. We would just keep the light turned on. But what if it were incrementing something? You know, if we were incrementing a value, every time you saw that number, it would increment. And it's not a new character. It's the old one. We've already processed it. So your assessment is exactly right.
Yeah.
Okay. Explain some more to me here.
All right. So like you were saying earlier, the rest of the code in Forever, we're looking to see if there are any other values of interest. The next one we're potentially interested in is the 1 character. If the value in register 16 is equal to the 1 character, then we're going to jump to the turn on code, which turns on our LED, and which is on port B5. And if that happens, then we go to the next code to kind of like reset for the next interrupt. And similarly, if we have a 2 character in our register, then we'll jump to the turn off code, which just turns off the LED, goes to next. And this will just keep looping through, basically processing interrupts as they come in.
Yeah, Robert's test was a really good one, which was put in multiple characters on the same line. Part of the reason that that's a good test is because we added no line endings down at the bottom right-hand corner there, which means normally as you type characters and you hit enter, it's throwing a line ending on it as well, which we wouldn't be processing. We would process it as a do-nothing character. But then when you type multiple things together, things could get a little strange if you try to make those mean something. And so by intentionally saying we're going to process every character or we're going to create every character, we give ourselves a little more freedom in the data. We don't always have control of the data stream. When we do, though, having it not produce extra characters that we can't see is usually a good thing. And then we'll get burned with that one later on. Maybe if I remember, I'll show you. It'll be a different lab, but I'll show you why you would want to normally leave that on. Okay, anybody else have any other questions, comments, or analyses? No? Okay. Okay, well, one of the things we need to do is we need to install, or I may have had you install it already, processing. Did I have that installed? Okay, why don't we start up processing? Not starting, it's just starting on a different screen. Notice how much this looks like the Arduino environment. Now, when we're running processing, because we're going to use it for very much the same things we were using the serial monitor for, you need to make sure that the serial monitor is not open. If it is, you'll get a conflict thing and it won't do the right stuff for you. And if this is open, you have to make sure that you don't try to use the serial monitor. So it's one or the other when we're using it. To test your install for this, you can do File, Examples. A little menu, a little nicer menu shows up here. It's kind of hard to move. I don't know, pick under image, pick pointillism. That would be a fun one. A new one will open so you can close the old one. And there's no compile on this, you can just run it. And I guess basically if something happens, you're in good shape. We could read the code to figure out what it's doing, but it makes beautiful art. Everybody get that to work? Yeah, I thought you would. Okay. Close that. You ever see a YouTube video by this guy? He's the wackiest dude in the world, but he's really smart. And he did a whole series on processing and on P5 and some other programs sometime. But I haven't seen him in years, but if you ever see him, he's worth watching. At least one of his videos. Okay, what I want to do is, let's close that for the moment. We know it works. So in our labs, go to lab, we're going to skip lab 3 for the moment. Go to lab 4P. There's two things. One is called button with LED. Don't click on that one. Click on the other one, lab4p.pde. And if all goes well, it should open up a window for you with one of our programs on it. Now, what I want you to do is just simply run this. You should get a screen that looks like this. If you didn't, we have one little bit of work for you to do. If you got the screen that looks like that, show me. Give me a green circle. Oh, you guys are good. Okay, now, the right-hand button, if you click on it, kind of flashes your Arduino board. If you look at the Arduino board, when you click the right-hand button, you'll see it received a character. However, on the left-hand button, if you click it, you'll see it not only received a character, it turned the LED on. Look at the second time, it turns it off. So this guy is basically doing what we did in the last program, but under the hood. This is sending a 1. This is sending a 2. Or, yeah, I guess it's a 2. This is a lot cooler interface. You can imagine that when we were able to hook all sorts of hardware and things to it, we can do some pretty fancy stuff. But this is code that I would expect you to be able to work in with something that works on the Arduino. We'll be doing some interesting things where you'll need to know how to do some processing. Processing is basically Java. Nothing particularly fancy about it. The documentation, did I point you at the documentation page? I probably didn't. Hang on here. It's not this one. We want the documentation from the older version. We're running an older version. Let me see. What version are we running? 3.5.4. Nope. Let me see if I've got it on here somewhere. No, I don't. I stumbled across it the other day, so let me see if I can find a. Well, we may be stuck with the new documentation. It won't be that different, but my old URLs have gone away. But this is where you find the functions and things that have been added. So it's basically as if you were writing in Swing or something else where they add a bunch of new functions. These are the functions. I simplify the grammar so that it's a little easier to use. And my guess is that all the old functions are still there. If I can run across the old documentation, I'll make sure I post it for you. I might have a downloaded copy of it. But if you look at this, things are not particularly tricky to use. We import a header. We create an object of types. It's a class of serial called sensor. We create a class that we created, an array of them called button with LED. That's one of these things. Some width, some heights, these are like constant variables. Then instead of having setup and loop, it has setup and draw as its two methods, much like Arduino did. Except here we're going to allow ourselves to use the processing. We call button with LED. We have some code that runs when mouse is pressed. We actually just call the mouse is pressed function on each of the buttons with an LED. And then here's the code that knows how to draw and make the button do the right stuff. So you're going to want to kind of study this to see what happens and how to make it work. But this is code that now belongs to you as well. When we need a reference and you need a button that also has an LED on it, notice this works when you hover over it. We get a different color than when we press it, we release it, remove ourselves. So it's got a lot of function added, which adds to the experience of the Arduino or the ATmega running for us. It gives us a nice way to write good utility functions. Now, if you didn't get it to work first try, one of the things to let me see if I can raise that somehow. When we run it, it should print out for you all of the ports that are available. So if I run this, I only have COM3 as a serial port. If you have more than one port, you need to look at the index number, and then inside the lab code, where you're creating the sensor, you need to make sure the number right there matches the correct device. So for instance, if you had 3 devices of 0, 1, and 2, but number 2 is the one that's really your Arduino, you would change this to be a 2. And all it's doing is it's creating a list right here, and then it's just using the one you set out of the list. Is anybody still having trouble? Mikhail, you have a question? I'm not hearing anything. Hey, Dominic, what problem are you having? Oh, Dominic's not here. Dante, I mean. Trying to read that across the room.
No, yeah, you answered it when you explained the whole the COM have to change the
Yeah,
serial dot
it
list.
might have to change.
Yeah.
Okay. Leslie, what's the problem with yours?
So Mikkel's saying that it's saying that the port is busy.
He's got his window open still in the other program. He's got to close the Arduino window.
Mine work fine for now. No.
Yeah. Okay. Mohammed, what's it, yours, or does that symbol mean that you jumped out the window? Okay, you're working. Anybody still not working? Okay, I'm sure among you, you're going to be able to figure out what isn't and what is working. One of the things that you can do with this in terms of studying this is just basically Java code. So if you think of it as a Java program that has this method and that method, and then a bunch of methods that implement the mouse interfaces, press, release, and move, that's really 2 interfaces. You'll be pretty good because internally they cover the rest of the things that are happening. An interesting piece of code in this is this button with LED, because in theory, although we may or may not have ever implemented it, you could play around by saying, well, I don't want 64, let me try it at 128. Let's see if they caught all the spots where that occurs. And they may not have. If I run that now, will I get 2 big fat buttons? And indeed I do. Do they work? Indeed they do. So some best practice type thing. This guy still turns the LED on my Arduino board. Now, for this to work, we have to make sure that lab 2 is loaded on the board. This is lab 4, that's lab 2. So you might want to write a note to yourself somewhere that says if you want to do that. Now, number of frames equals 3. We'll start on frame 2. Aha! This tells me something. That means they're animating something. Let me go look in the code. In the data thing, look what's there. There's a PNG file with all 3 animated frames. I'm sure the white in the back is probably transparent. If I wanted to add another state to my button, or I wanted to change the design of my button, maybe instead of this on-off looking thing, I wanted to put the picture of a dinosaur there or the picture of a cockroach. I could do something very interesting on my button and still have a button which did all the right functions. If I wanted to make it have 4 items, I'm sure somebody else is doing the number of frames, but they're probably not going to ever pick the 4th frame in their code. So you could go through here, it's going to obviously create the frames, but then when you use them, is it going to use a new frame? Probably not, because it calls out the frame by number and says what to do if it was 1 and we release the mouse. So you'd have to rework the navigation code, but that could be fun to do. I mean, writing a good interface can be as much fun sometimes as writing the code that you're controlling, writing the device you're controlling. But what this gives us now is the ability to modify the hardware that's running the ATmega code, and as a result of it changing, send us data on the PC so we could display it. Remember, that's what we did with the name. We also have the ability to take and send data from the PC to the ATmega chip so we could control something out there in the world. So we could make the ATmega controlling a lock. We could build a little keypad that on the PC, we'd have to type the right combination of keys in order to unlock the lock. We'd have to symbolize it in this class. We might do that later. We'd have to symbolize that in this class by simply being rewarded when the LED turned on, because we know we could simply turn on a transistor, which could turn on a lock, which could turn on the world. Receiving something, that could be the result of pushing a real button somewhere, could cause us to see the input. So there's a lot of worlds that we've represented by just having a single LED and a way to display something. And by having processing on our side, so we can demonstrate things that literally work and demonstrate it would work if we had hooked it up, we'd be able then to build something. So some of you that are a little electronic enabled, maybe you own a perf board or a switch or an LED, you could extend some of these exercises to demonstrate to yourself that you know how you would make that happen. Each of the pins can roughly support, I wouldn't push it at more than about 20 milliamps. The book will tell you it can do more, but because there's a grand total across the entire board, you don't want to burn up your board. And I would limit myself to 20 milliamps. So I could control an LED with a single pin, but I probably don't want to control 25 LEDs with a pin, because that's 25 times 20 milliamps, which would probably exceed the board's input capability from your USB port. And wherever it's coming from the USB port, anything you control. So you want to be a little careful with that. Mikhail, you have a comment? Or is your hand still just up? Yeah, I'm still not hearing you. Okay, let's take a walk through this code and just make sure we understand what's going on. Not that I don't think you could do it on yourself, but I think it might be useful to have looked at. So, and actually, let me put this back to what it was. This was 64. That was 64. Okay, we're going to create an object which represents a serial port. This is a built-in object that we'd find on that reference page. We're calling it sensor because we want it to stand for any arbitrary sensor that we've converted into just being able to send us ASCII data. We then want to create the 3 buttons that are going to be, or 2 buttons that are going to be used on the screen. Just create an array of those. Some values that tell us a little bit about the size of the buttons. Now we need to know that for separation purposes. If I went over here and I changed this to be 120, well, we did that, didn't we? 256. and I reran, I'm going to come into this unfortunate circumstance here. Notice I got some middle ground that I can get both buttons at the same time. Some outside thing. But notice they overlap uncomfortably. Oops, what did I do? Hopefully I didn't delete anything too awful there. So it probably was a bad idea to hard code these. It should have gotten it from the buttons themselves because there's nothing that says this button's the same size either. But for the purposes of the example, I think it's probably okay. Then we want to assume where X is because the buttons are side by side for the two buttons that we have. It's basically the width of the screen divided by 2 minus the width of a button is where the first one is. And the other one is relative to where X1 is plus 2 times the width. So at normal width, that leaves us some space between. And we want them about halfway down the screen. We know what the size of the screen, again, Y is the top of the button, top left. So we don't use the size of the screen directly, otherwise it'll look like it's in the wrong position, it'll look a little low. We set the size. Size must be the first parameter of a setup function if you're going to set the size. Then we simply print out the array, which is the list of all the serial ports. Then we get the individual sensor we want to be working on by creating a new sensor, passing it our object, which is going to be the thing we're using, and from the serial port, the one that is literally the Arduino, and a baud rate. Now we actually create our 2 buttons and call setup on each of them. What their setup functions do, they have a bunch of things that they need to have also. They need to have a height and a width. They need to have a number of frames and which frame we're currently on, and a set of images of those frames, as well as the current image we're showing. Where the X and Y are, what their width and height are for drawing purposes, where the LED is that's sitting behind them and just peeking out at the top, and what the fill color of the LED is when we turn it on. And is it on or off? Now the constructor for each simply figures out where its X and Y is by taking its width and height and dividing it by 2. We need to know where that corner is because that was given to us initially. We need to, because it's the center of the box, we need to find the top left corner. Here's the setup method, gets called on each. We load the image and load the pixels of that image so we can extract them from it. Then we create an image where the width of it is basically the number of frames divided to get which one of the 3 we're going to be using, which frame is it, pull it out of the image of pixels we have. And also then, after we've created the image, we're going to get the actual frame so that we have that frame available to us. We'll put that into the index number. So that loads up the frames for us for that particular button. Remember, they're going to be identical for the 2 buttons, but we nevertheless do it twice. Then finally, where the LED, it needs to be put into its correct spot. Ultimately, draw gets called. Draw simple. Set the background color. I used a nice color. And then we draw each of the buttons. That's why this one was on top of that one when they were too wide. Draw doesn't do much. Sets the stroke size, which 0 means as narrow as you can be. Set the fill color. Set the mode for the rectangle, meaning the address I'm given is going to be the center of the box, not the corner. We'll draw the rectangle, XY, what its width is, its height is. And I forget what the 8 even means on this one. It may have to do with the size of the rectangle, the line we're drawing. I don't remember. You have to look that up. And then the image is placed into the frame at each of those button positions. Then for every button press, we have what happens on pressed, what happens on released or moved. And basically what we're going to do is check to see, is the mouse currently in this rectangle? If it is, display this frame, set the LED either true or false, depending on whether or not we have the LED value set to be true or false, and then set the fill color. Mouse and rect, we check the frame. Mouse and moved again, we check to see if it's in the rect. Here's a simple check of, are we in the rectangle? And I'll let you look at that and determine why that works. And then those all get called for each button. So if we have a mouse press detected, we call each of those, and when we're done, then we decide what to do about sending a piece of data. We send either a 0 or a 1, depending on what the LED is. Well, I'm sorry, this is the initial value. We set a 1 or a 0 if this comes back to not be true or false, which we know can't be. And that supported some older code that has been taken out. That probably doesn't do anything anymore except introduce value as a variable. And then we call released or moved, depending on which of the ones we've detected at the higher level. So you might poke around at this, make a few changes. If you make changes to it, keep the original so you can run it again. But have fun, knock yourself out. Maybe change what the pictures look like a little bit by editing these pictures, the frames. Make yourself very familiar with using processing and the ATmega chip at the same time. They're the two halves of something very useful. So what we basically can do is the ATmega 328P and receive ASCII commands from processing. In the ATmega 328P, and send commands, ASCII, haven't seen them yet, to processing. Now, we haven't done anything with that yet, but we've seen that we could send it back and print it in Arduino's serial monitor. So most surely we'd somehow be able to receive and processing data. Difference there is receiving is harder than sending, because when you receive, you have to handle the case, what if I receive something while I'm receiving something else? What do I do if I receive invalid data? Whereas if I'm sending data, then it's, or where I'm just receiving it here in the ATmega, we've already solved that on this side of the world. We haven't solved it over here. We will next time, I'm sure. Anybody have any final questions? Okay, make sure you spend some time. If you saw instructions and things you don't know, this is now the time to go review those in your documentation. Remember, we got that huge section at the end of the book. You go over on the left, instruction set summary. Find those instructions we used today. Make sure you know what they do, because it's not that long till we have to turn you loose. What did I see a red box for? A red circle.
We lost you for a second, I think.
You lost me for a second? Okay, I'm back. Okay, thank you. Yeah, make sure you go through this set of things, particularly the instructions we used tonight, and think about the way we protected our data using interrupts. We have this thing that can happen at any time, but nevertheless, we protected code that cared. Okay, I think that's good enough for tonight. I shall see you fine folk on Wednesday night. Be on time. Could be lots of fun. And we'll, I'm sure, do a couple more labs before we get, too involved in studying the details of, well, we probably will study the detail of some of the timers in the next class. So you might want to start running your eyes over those. They're complex, so I don't want you to think you have to read every word of those to understand them. You don't. But if you get bored, it's a great thing to look at. Okay, I'll see you people on Wednesday night. Have a nice time until then. You too.
Professor.
Good night,
Bye-bye.
Professor.
Good
Yeah.
night.
Good night, Professor.
Good night, Professor.
Good
Bye,
night,
Professor.
Professor.
Bye-bye. Y'all